We're going to spend a few minutes now talking about ions and how how an atom being ionized affects its radius, as well as talking about how it affects its electron configuration. So, just real briefly here, if we take a look at these pairs of atom and ion, or two ions in the case of this one here, which one of the pairs do you think is going to have, or is going to be the larger atom? So go ahead and pause the video if you would like to try and figure it out on your own. Pause it and pick your choices for the larger particles. All right, our basic principle when it comes to ions is, does it have more electrons? If it does, it's going to be a little bit bigger. Does it have fewer electrons? If it has fewer electrons, it's going to be smaller. And it does vary a bit from one element to the next. Some it varies a lot, but usually the percent change is a lot larger in cations. Usually cations are a lot smaller than just the plain old atom, the non-ionized version, and the anions are not quite as dramatic usually. But just to give you the answers for each of these here, chloride has more electrons, and so it is larger. Sodium is larger than sodium plus. Iron is larger than iron plus. In both of these, because they've lost electrons, they've actually lost all of their valence electrons, and so they are much smaller as cations. In this one here, Fe3 plus is smaller, so I don't know why I wrote that one. I should say this one is larger. Fe2 plus is larger, and then O2 minus is the larger of the two here. It has more electrons, and so it is larger. And so you can see that here on this, I guess you could call it a figure. So you can see here the group 1 metals, when you ionize them, you go from lithium to lithium plus, it is a lot smaller. It is less than half the size of lithium, is lithium plus. And most of these are around in that range, about half or a little bit more than half. So like with boron 3 plus, that's about a quarter, maybe a little bit more than a quarter the size, boron 3 plus is versus boron. So the cations tend to be quite a bit smaller. Anions, it's usually around, like the maximum is around twice as big, whereas the maximum was more than half here. The maximum with the anions is around twice as big. It's pretty much as big as it goes, but they are bigger, anions, versus the neutrally charged atoms. And so just a couple other examples here real quick. So sulfur versus sulfide. Sulfide is going to be bigger. It has more electrons. Calcium versus calcium 2 plus. Calcium is bigger. It has more electrons. This one's a little bit tougher. We have bromide versus krypton. If you look up where those things are on the periodic table, they are right next to each other on the periodic table. So bromine is element number 35, so this would have 36 electrons, and krypton has 36 electrons. So we can't go based on the number of electrons. If we think about it in terms of the location on the periodic table, because they're both on the same period, one of them is not higher or lower, so we would have to work on the left-right trend, which would make us believe that, let's see, bromine is to the left, and so bromine should be smaller based on that trend. But keep in mind that that is just looking at neutral elements. Another thing that is different here is that we have an extra electron with the bromine for one thing, but also the number of protons is different. So they have the same number of protons, the same number of electrons, but the number of protons is different. This has 35 protons, and this has 36 protons. And so the krypton, because it has more protons, is going to be it's going to have a larger pull on the outer electrons. And so the krypton, based on that, is going to be smaller, which I guess is what I just said a second ago. So both of those trends would actually agree with one another. So the trend that the stuff on the left is larger agrees with the second way of checking this, which is thinking about how many protons does this have. And so the larger number of protons in krypton would compress the atom even more because it's going to pull on the outer electrons even more. The bromide is larger. The krypton is smaller. All right. So moving on, last thing we're going to talk about in this video here is how having an element ionizing an element, how that changes the electron configuration for that element. Now when it comes to anions, this is pretty straightforward. With anions, because you're adding in extra electrons, you're just going to stick extra electrons at the end of the configuration. So if you have something like, let's see, oxygen. See if I have space back here. Yeah, so oxygen, if we had oxygen 2 minus, oxygen has 8 electrons, and so we would add 2 extra to give us 10, and so it would just be 1s2, 2s2, 2p, and if we would just had the unionized oxygen, we would only get up to 2p4, but since we have 10, it will be 2p6. We have 2 extra, and so we get to fill that 2p all the way up. So with anions, it's pretty straightforward. Just however many extra electrons you have, just tack those on to the end like normal. With cations, it is sometimes a bit different. With cations, what this means, if you have something that has lost electrons, those electrons didn't just disappear from existence. Something came along and took it. Something took those electrons. And so because something had to come along and take the electrons, that means that the electrons that were stolen had to come from the valence shell. Because those are the only electrons that are available for other stuff to interact with. Those are the ones that are the farthest away from the nucleus. So when we have something like iron 2+, iron has this electron configuration in its normal non-ionized state. But when you take 2 electrons away, you don't take them out of the 3D, even those are the highest energy electrons. Where they leave is from the 4s. That's where they leave from, because the 4s are the farthest out from the nucleus. And so those are the electrons that will be taken if something ionizes iron. Now, as soon as those 2 are taken, if something else comes along and takes another one, so if we have iron 3+, for example, well then yes, we just do start at the highest energy and work our way down. But we always take the electrons from the highest principal shell, from the valence electrons first, not necessarily from the highest energy, from the highest valence shell, so the highest principal shell. All right. And then just real briefly here before we do a couple orbital diagrams, oftentimes when we're looking at ions and considering the electron configuration for ions, we're going to be looking to see if we have unpaired electrons or if all the electrons are paired up. If we have an electron configuration where everything is paired up, This is what we call a diamagnetic electron configuration. So that is a diamagnetic material. If all of the electrons are paired. If, on the other hand, we have any unpaired electrons, even just one, if we have any unpaired electrons, that will be a paramagnetic material, and it will be attracted to magnetic fields. So anything that is magnetic, it has unpaired electrons. This is one of the reasons why iron is such a good material for magnets, is because especially iron, when it's in a certain oxidation state, got lots of unpaired electrons. So anything that has unpaired electrons is paramagnetic. It's attracted to magnetic fields. Anything that has all paired electrons, that is actually going to slightly repel magnetic fields, and those are diamagnetic. So real quickly here, let's draw some orbital diagrams. I would encourage you to pause the video here and try to work these out yourself, and then come back and see what I get from working these out. So please stop the video now and then come back. Alright, so when I'm writing an electron configuration for an ion, I usually, just because it usually makes my life a little bit easier, I go ahead and write the electron configuration for the non-ionized atom first, and then make the changes from there. If I'm very deliberate in doing it that way, I will usually always remember to take the electrons out correctly when I'm doing cations. Sometimes if you try to do it quickly, you can forget and just leave the electrons off the end, which is not always going to give you the correct answer. So with aluminum, for example, aluminum is element number 13. So I'm going to go ahead and write the configuration for 13 electrons, and then I'm going to take it down to 10. So with 13 electrons, and actually what I think I'll do is I'll write the electron configuration, and then I'll do the orbital diagram just for the ionized version. So I'll do the normal version with the electron configuration. So 13 electrons would be 1s2, 2s2, 2p6, that's 10, 3s2 is 12, and then 3p1 gives me 13. So in this case, the highest energy electrons are also the valence electrons. So when I write my orbital diagram, I'm going to have those three not show up because they have been taken away by something. So my orbital diagram would then be 1s with 2 electrons, 2s with 2 electrons, and then 2p with 6. Now I did this a little bit differently than I've done in the past. That's just because I knew how it was going to end. If I was just filling it out not knowing what was going to happen, if I hadn't already done it up here, I would go ahead and fill them in singly, and I would write out more than just the one that I was working on at the time. But since I already had the configuration, I knew how it was going to end. So similar thing here with sulfide. Sulfur is number 16 on the periodic table, so this is going to have 18 electrons. Because this is an anion, I don't have to worry about putting the electrons in a certain spot. I'm just going to stick them on the end. So the electron configuration is going to look like 1s2, 2s2, 2p6, there's 10, 3s2, 3p6 is 18. So then the orbital diagram is 1s, 2s, 2p, 3s, and then the 3p is also completely full. Alright, so then the last one here. iron 3 plus. Iron is element number 26. I'm going to go ahead and write the electron configuration for regular iron. So we'll have 1s2, 2s2, 2p6, 3s2, 3p6. What's after 3p? Not 3d, 4s, 2. And then 3d, if I see how many I have so far, I have 10, 20. Iron in its unionized state has 26, so I'm going to go ahead and put all of those 6 here. So this is the unionized iron. Again, the reason why I'm doing this is because if instead I just put 23 electrons in, I would end up with 3d3, which is not correct. Because remember, you take the electrons from the valence shell first, and that would be the 4s. That is valence. So my actual configuration is this being gone, and that not being 6, but being 5 instead. So we take 2 from the 4s, and then the last one comes from the 3d. So then my orbital diagram is going to be, boy, that's kind of small. Let me do that again. So it's going to be 1s, 2s, 2p, 3p, 4s, 1, 2, 3, 4 lines gives me 5 different orbitals. Alright, so that one's full, that one's full, this one I know is full, 3s is full, 3p is full, 4s is empty. And then we have 1, 2, 3, 4, 5 electrons, all in their own orbitals with parallel spins. All right, call it there for this video. The next one we'll talk about, briefly, talk about electronegativity. We'll get more into electronegativity in Chapter 7, I believe. I'll see you in the next video.